Dear students, in this lecture, we will discuss about the statistical interpretation. Suppose there is a particle, and this particle, by its nature, is localized at this point, and there is a wave always associated with this particle, and this wave you can see is spread out in space, and this wave is represented by psi as a function of position and time. What does this wave function mean? This wave function of a particle at any particular time contain all information about the particle, but this wave function itself has no physical interpretation. However, according to Born, square modulus of this wave function has a physical interpretation. It means that square modulus of the wave functions gives the probability of finding the particle between some limits at time t. Please note that the probability is nothing but area under the graph of square modulus. Suppose here is a typical wave function where the shaded area representing the probability of finding the particle between A and B, and that is mathematically can be written as P equals integration from A up to B square modulus Px. For this wave function, the particle would be relatively likely to be found near A and less likely to be found near B. You know, the amplitude of square modulus is higher at point A comparatively to the other points. But still, even if the theory tells you all about the particle, you can't be certain about the position of the particle. Quantum mechanics gives you statistical information about the possible results, but the statistical interpretation introduces a kind of indeterminacy in quantum mechanics. So, question is, why is it so? Is it a fault of theory or a fault of measurement, or is it a fact of nature? Let's start discussion to answer these questions. Suppose we find the particle at point C. Okay, then where was the particle before measurement? To answer this question, there are three types of school of thoughts. First, the realist. The realist says that the particle was at C. What does this mean? It means the particle really was at C, and quantum mechanics was unable to answer this question. It means quantum mechanics is incomplete theory. Because the realist believes that the indeterminacy is not a fact of nature, but a reflection of ignorance. Means that psi is not the whole story. There's some additional information needed to provide along with the psi to completely describe the particle's position. And the second approach was orthodox. According to them, the particle was not really anywhere. It was actually the act of measurement that forced the particle to take a stand. According to them, observations not only disturb what is to be measured, they produce it. Hence, we compel the particle to assume a definite position. This is also called Copenhagen interpretation. And the third approach was of agnostic. According to them, they simply says it is a metaphysics to worry about something that can't, by its nature, to be tested. So hence, simply they refuse to answer this question. Okay. To check experimentally, in 1964, Bell rooted out the agnosticism by performing experiment to test 1 and 2. And the Bell comes up with the conclusion that orthodox is correct and quantum mechanics is a complete theory. Even if someone made second measurement immediately after the first one, a repeated measurement must return the same answer. Here we comes up with the new concept, that is a collapse of wave function. Because the wave function was spread out throughout the space. I mean, if I take you back to the wave function, this one, where you can see the wave function is spread out throughout the space, and once we measure the particle's position and we come to the conclusion after the measurement that the particle at point C, then this whole wave function collapses at point C, and the wave function comes up with the new phase, and that is exactly like this, where you can simply say that by measuring the particle at point C, actually the wave function collapses at point C, and this is happened by the first measurement. Hence, probability of finding the particle is maximum at point C and zero elsewhere.